Okay, good morning, everybody. Today we're going to be doing more with our statistics and our probability. This is lesson 5.2, day 1. And here we're going to start to bridge the gap between theoretical probability and this kind of simulations or the empirical probabilities that we've been doing before. So let's go ahead and take a look at what we have today. And we're going to play a dice game here. The question that we're going to answer is odds or evens. Who will win? So you and your partner is going to decide who's going to be the odds and who's going to be the evens. We're not going to worry too much about that for this. So we're going to roll 2 dice and we're going to multiply the numbers. And if the product is odd, the odd person wins, and the vice versa for the evens. So we're going to do this 20 times and we're going to see how many times each person wins. So I'm looking ahead just a little bit here, and it just says how many times did the odds person win. So really we're just going to be concerned about the odds. So how many times does, when you multiply, will we get an odd result? Now Google has a nice thing that you can use to roll dice. I just Googled virtual dice, and I'm going to put 2 of them on the board. We're going to multiply them. That's 24. So, yeah, not a win. 24. Second roll, that's 15. That's 1 win. Third roll, 24 again. 1 times 3 is 3. So that's 2 wins. 2 out of 4. 2 out of 5. 2 times 8 is even, so 2 out of 6. 2 out of 7. 2 out of 8. Wow, the even person is really racking it in here. 2 out of 8. 3 out of 9. 3 out of 10. 1 times 6 is 6, so 3 out of 11. 3 out of 12. 3 times 4 is 12, so 3 of 9, or 3 of 13. 3 of 14. 5 times 6 is even. Oh, here we go. 4 of 16. Ooh, 5 of 17. 5 of 18, 6 of 19, and 6 out of 20 times our odd person won. So our odd person wins 6 times. We're going to write that as a fraction out of 20 and turn that into a percentage. 6 of 20 equals 0.3, and that's 30%. So, whoever got even clearly got the better end of the deal here. Or not. Maybe it was just bad luck. So that's one thing that could happen. Maybe we just happened to roll a lot of even on our dice. So let's see how the rest of the class did with the odds. And so we're going to run into a simulation to see how the rest of the class did. As you might suspect, I kind of tried to automate this. So here on the left side, we have a bunch of dice rolls. Let's see if we can zoom in here. There we go. Over here on the left side, so roll number 1, dice 1 got a 2, dice 2 got a 6, and when we multiply them, we get a 4. We do that 20 times. 20th trial here was 1 and 2, which is a 2. And then we're just going to count how many odds results do we have there. We turn that into a percentage, 5%. 1 out of 20 is 5%. And yeah, that's all we really need to do. So in order to create a class set, I'm going to do 5 of them. So this first one, we have 4 odd wins. This next one we have 7 odd wins. The next one after that we did 4 odd wins and 5. And lastly, the odds won 3 times. So that is interesting. I'm going to go ahead and turn those into percentages. And what we did after this is we kept track of the percentage of total wins that the odds got. So once we got to, let's say, a good class size is like 36. So how many odd wins do we have? We have about 25.3 times the odds won. So that's going to be for our class. Let's outline that. Yep, 25.3. So how many for the whole class? Well, for my virtual class, we got 25.3% odd wins. So how does this compare with our group's results? Well, this is a bit lower than our group's results. But I think the thing I want to say is it's not really that far off, really, 30 to 25%. So pretty close though. And so that was our simulation part. The next part here is we want to determine the true probability of rolling an odd product. So we're going to list the numbers that we can. So here's what we have. On the top row here, we've got die number 1. Side row over here, we've got die number 2. Now, die 1 and die 2 are the only 2 factors that come into play as we roll dice. Nothing else could possibly happen. So if I list both of these dice here and I look at their combinations, then I create what we call the sample set, or the all of the possible outcomes between these 2 dies. And what are we interested in? We're interested in what if we multiply the 2 dies together. So what if we multiply 1, if the first die, the yellow die, gets a 1 and the blue die gets a 1, we're going to multiply them, and our outcome there, that's going to be a 1. 1 times 2, that's a 2. So that means that the blue die rolled a 1, the yellow die rolled a 2, we got a 2. If the blue die has a 1 and the yellow die has a 3, then our outcome will be a 3, and then etc. Okay, so that's everything that could happen if the blue die rolls a 1. But what if the blue die rolls a 2? What happens now? Well, if the blue die rolls a 1, a 2, and the yellow die rolls a 1, we're going to get a 2. And then we just keep multiplying. Blue 2, yellow 2 is a 4. Blue 2 and yellow 3. That's a 6, 8, 10, and 12. So hopefully what you're seeing is that we're actually creating a multiplication table for the numbers from 1 to 6. So why don't we go ahead and just create our multiplication table. That's all of our outcomes. Now that we have all of our outcomes, first thing we're going to do is count how many of them there are. And there are 6 times 6, there are 36 different outcomes that could possibly happen with 2 dice. One of them is the yellow die, the other one is the blue die. Then we're going to ask, how many of those outcomes are odd outcomes? Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. That should be it. There are no other odd numbers in our table. So there are 9 outcomes that are odd, divided by, or out of, 36 total outcomes. So 9 out of 36. That's equal to 0.25, which is 25%. So, which was closer to the percentage you found in number 4? The group data or the classroom data? Well, the group data was 30 and the classroom data was 25. So it seems as though the classroom data is closer. And why is that? Well, there was definitely more outcomes. There was more trials, which meant we had more data, which means we are able more to unlock that law of large numbers. Now, as a little extra that we did here is I didn't actually stop at 36 different trials. I actually had a classroom of 100. I should say a virtual classroom at 100. And take a look at that percentage. That is 25.2%. That's really close. Even though in our classroom data, we were also really close. We got to 25.3. So you can see we didn't necessarily need to get all the way to 100 in order to figure it out. And as a little bit of extra for you, I also created a wonderful little line plot. So we can see how that percentage, how it actually worked. So over here, we can see that in the short run, it was very unpredictable. But eventually, this kind of settled down into this, basically, if you're really mathy, you would call that a horizontal asymptote right at 25%. And we got to there pretty soon, right around 40. There's a little dip here, but starting around around 50, it was pretty stable around that 25%. We can just copy that over here just for us to see. And then now that we have our theoretical probability, we can use the table to find the probability of rolling each of the products. All we need to do is count the number of outcomes and divide by the total number of outcomes. So let's take a look at question 6a, a 4 or a 5. Let's highlight how many times do we see a 4 or a 5. 1, 2, 3. Do you see any 4s or 5? Oh, there's a couple of 4s and 5s. Do we see any other 5s? No, that's it. So there are only 5 different ways that we can get a 4 or a 5. So how many different ways were there to get a 4? To get a 4, that was 3 out of 36. How many different ways were there of getting a 5? That was only 2 out of 36. How many ways were there to get a 4 or a 5? That's equal to 3 plus 2, or 3 plus 2 out of 36, which is 0.13. And I think I want to write it more like this. So if we do a probability of a 4 or a 5, all we need to do is find the probability of a 4, then find the probability of getting a 5, and then add those together. So that gives me 13.9%. Now be a little bit careful when using this rule. We'll definitely talk about that a little bit more. But 4 and 5 are what we would call mutually exclusive outcomes. In other words, an outcome from our table can't be both a 4 and a 5. It's got to be either one or the other. Now, the other way of doing this, which I quite like, is just to figure out all the outcomes, which are a 4 or a 5. So there are 5 outcomes out of 36 that are either a 4 or a 5. So 5 out of 36, that gives us that one anyways. Okay, how about a number besides 6? Well, there's a lot of outcomes here that are not a 6, but there are only a few outcomes that are 6s. Let's see, the 6 outcomes are this one, this one, this one, and this one. So right now we can say the probability of a 6 is, the outcome of a 6 is 4 out of 36. Well, an outcome either is a 6 or it's not a 6. So these are what we would call complementary, one or the other, either a 6 or not a 6. So if I want to find the probability of not a 6, so the probability of not a 6 is 1 minus 4 out of 36. And you might want to think about that as 36 out of 36 minus 4 out of 36. So it's all the outcomes minus the 4 that correspond to a 6. And that gives us that 32 out of 36, which is 88.9%. This is called a complementary. Whenever we find our probability by subtracting from 1, finding all of the undesirables and subtracting them from all of the entire set, we call that a complementary set. So here, we want everything but the 6, so we subtract from 1 to find out everything that is not a 6. So we find out first how many 6s are there, then we subtract it from the total number of outcomes, and that gives us this 32. This process of subtracting from the total number of outcomes, that's what I mean by a complement. And then this last one would be any number between 1 and 36. Well, all of the outcomes are out of 36, or are less than or equal to 36. So if we're describing everything, then that's 100%. And that's just basically all the probabilities that we ever do if we have the entire sample space. That's the word I've been struggling to find, sample space. If we find the entire sample space, everything has to add up to 100%. That brings us to our important ideas. So the first one is a probability model. And in our probability model, it's just a list of all the possible outcomes and their probabilities. This one right here, this was our probability model. All of the outcomes are from 1 to 36. There are no other outcomes that could happen other than these. So these numbers right here make up our sample space. Okay. So probabilities, we usually note them as a capital P with a parenthesis and the outcome, and then it's equal to a probability. Probability is a 4-decimal number for our class. Unless the ending decimals are a 0, please put 4 decimal places here. Incidentally, I don't prefer that you make this abstract. Don't give me probability of A. Tell me the probability of pizza for dinner is 0.1125. That's what I want to read. I don't want to read A. All the probabilities have to add up to 1. We talked about that, of course, because that means 100%. And then all probabilities have to be a number between 0 and 1. We did this thing about the complement. We notate the complement with P of the event with a that looks like an exponent C. So superscript C. Okay, and it tells you the probability of an event not happening. So when you see probability of A complement, that's the probability that A doesn't happen, and that's 1 minus the probability that A does happen. Now, there's this idea of mutually exclusive, and the sooner that we kind of really understand what that means, the better it's going to be for all of us, because another concept's going to come around, and you're going to confuse the two. So the first concept, which you must not confuse, is mutually exclusive. Those are when two events cannot occur together. We did 4 and 5 before, so we cannot have an outcome, or we can't roll 2 dice and get both a 4 and a 5. It's either one or the other, never both a 4 and a 5. That's what we mean by mutually exclusive. The general addition rule, which we looked at before, would be if you need the probability of 2 events, you just add them. there is new symbols here, and it is this uppercase U. Technically, it stands for a union, but you can just think of it as an OR. So the probability of A or B is the probability of A plus the probability of B, provided that A and B are mutually exclusive. So you can see this starting to get already a little bit fuzzy. All right, let's check our understanding here. Let's suppose that we tear open the corner of an M&M's milk chocolate candy, pour one candy into our hand, and observe the color. According to Mars, the maker of M&M's, the probability model for a bag from Cleveland factory is as given. Explain why this is a valid probability model. So two things have to be true. Firstly, all the probabilities have to be between 0 and 1. And as you can tell, these are all between 0 and 1. All probabilities have to add up to 1 is the second thing that has to be true. And we can check that real quick by adding everything together. And let's get this last one here. 1, 2, 4. And when we add them together, we get, oh, imagine that, we get 100%. So that's good. Can we explain why red and blue are mutually exclusive M&Ms? Yeah, that's easy. There are no M&Ms that are both red and blue. And we're talking about a single M&M that is colored red and blue. So that, I don't know what that would look like. Maybe red on one side and blue on the other. There are no M&Ms like that. M&Ms are either red or blue, not both of them. Next, let's find the probability that we don't get a blue M&M. That's the complement rule. And we can see that that's a complement rule because we're saying that we don't get a blue M&M. You can notate that with the probability of blue complement. Remember, that's that superscript C. Remember, that's equal to 1 minus the probability of getting a blue M&M. And that's 1 minus 0.207, or 0.793. What's the probability that we get an orange or a brown M&M? Well, first, let's check mutually exclusive, because we see the word or. So first, we'll check there are no M&Ms that are both orange and brown, which means that they are mutually exclusive. So the probability of orange or brown, that's equal to the probability of orange plus the probability of brown. Going back up to my table, we see that orange is 205 and brown is 124. So we're going to add those together and we get 0.329. And I think this is it. What's the probability that we don't get a red or a green? Well, let's find the probability of red or green first. The probability of a red or a green is 198 and 131. Okay, so that's 0.329. So the probability of don't get a red or a green, that would be the complement of red or green. So the probability that we don't get a red or green. Well, that's equivalent of 1 minus 0.329, which is 0.671. Now, the last thing I want to leave you with is this was not the only way to do this problem. So what is an outcome that is not red or green? Well, that would be blue, orange, yellow, and brown. So equivalent here, this is also equivalent to the probability of blue or orange or yellow or brown. And that's equivalent to 0.207 plus 0.205 plus 135 plus 124. And look at that, that's the same 0.671. So sometimes there are more than one ways in which to figure out these probabilities. So that is it for today. Again, this is the beginning of our probability. I know at the end there's a lot of like weird language letter soup. So, you know, we'll have to practice. You'll have to practice in order to get all of that kind of straightened out in your brain. And we'll see you next time here for more stats. Have a good one.